Hi, my name is Armand Deburi, and thanks for watching this presentation, which is going to be about closed form solution for the finite-horizon linear quadratic control problem of linear fractional order systems. This is a general layout for this presentation. Initially, I will start with the fractional calculus and defining some fractional operators and showing the application. Then I will show you the general problem statement and what would be the issue with the current method that exists to solve this problem. And it will be followed by the proposed method, and we will show the advantage of the proposed method in an illustrative example. You might think that the fractional calculus is a new topic, but indeed the born of the fractional calculus is going back to 1695 when the Leibniz was proposing the Leibniz rule. At that time, L'Hopital was asking Leibniz what would be the meaning of a half differentiation of the function. Leibniz replied, "It leads to a paradox from which one day useful consequences will be drawn." And he was right. After a century, there were a lot of applications, especially Abel's integral, that they could be easily solved in the framework of the fractional calculus. You might think that or ask that, what would be the definition of the fractional integral? The basic definition of the fractional integral is coming from the n-fold Cauchy integrals. The nth integral of a function such as x, it is going to be explicitly shown by this expression in the right hand side of the equation, which is associated with the factorial operators. If we let this n becomes any fractions, we can replace that with a gamma function. And also we are stuck with an arbitrary number a, which is indicating the length of the memory for that system. And this is called as a Riemann-Liouville fractional integral. The fractional derivative, the most common definition, it is going to be the Caputo definitions. And we have two types of definitions for Caputo. We have left-sided and we have right-sided. In general, fractional operators, they are going to have a left-sided and right-sided definition. And that is going to be pre-multiplication of the integer derivative operator with the fractional integral operators. And since we need the integration by part and in our method, you can see that the integration by part for the fractional derivative is going to be different from the fractional calculus by this expression. We are going to have this huge summation term, which is going to make everything complicated. The application of fractional calculus can appear in two ways. One, it can come from the nature of the physics, like as Abel's integral, which we ended up to having some integral with the singular kernel, like in the box that is being shown in the box. Or we can just give an example of non-Fickian diffusion, which has ended up to become like a fractional derivative. Or we can just enhance our model with these fractional operators to get the better performance. And it can be like using in a dynamic process that it has a memory or hereditary and add this kernel to absorb the memory. Or you can use it for your controllers, such as a fractional PID controllers. So speaking of that chart, I just give a couple of examples here. So this is Abel's throwing a stone in a potential field. So we are trying to determine the trajectory of this particle, and after just using the laws of conservation of energy and just using the physics, we can end up to have this expression. As you see in this green box, it just reminds us that this is going to be the fractional derivative of that function y, which can be easily solved using the property of the fractional calculus, or using the single Volterra equations to preserve the hereditary of the population models. This is going to be a type of like fractional operators that can be found in the standard fractional calculus textbooks. Or there are two more examples that I have worked on that recently, such as the dynamical system with the memory, and that would be like a creep behavior of the epoxy. As you see, we have this black line which is showing the creep behavior of the epoxy, and it's experimental data, and we're trying to fit a model on that. So we can just use a regular transfer function to do that, but as you see, it is not going to be a perfect fit. Or we can just add a fractional term into this transfer function, and you can see that we are getting the best fit. Or you can just use it and your controller. So adding these two parameters is going to give you a much better performance, this red line, compared to the other controllers. What it should be noted here is that these two parameters, they are going to have a properties that cannot be replicated by using a regular controller, even with like a very large number of parameters. So that is unique about this fractional controllers. Getting back to our original problem. So we have this linear time invariant fractional order system, and we are trying to choose the u such that we minimize this cost function in equation number 3, which is going to be a finite horizon type, since the TF is going to be bounded. We will follow the same idea that we have for the LQR controller. So we are defining this as Lagrange multipliers and the new cost function, and try to choose this lambda such that we can vanish this actually L star at the optimum trajectory. So doing for that purpose, we need to do the integration by parts, and we ended up to having this 3 equation subjected to this final terminal equation 6. Obviously, solving all these 3 equations associated with this final terminal, it is not going to be easy, or even it is impossible. You have to use a nonlinear programming techniques to be able to solve all these problems, and that is actually the main issue for fractional order system optimal control optimal control problem for fractional order systems. So you might think that we can use a technique to define a Riccati equation by defining this positive 7-definite function p, and put it inside of the equation, and ended up to having this fractional differential equations. But again, you can see that we have this infinite number of terms series inside of this differential equation, which is actually causing that you will not be able to solve this problem easily. So there is no Riccati equation for fractional order systems. Okay, so how we are approaching this problem and how we can solve this problem. So what we're going to do is, first, we're assuming that the solution and the input, they are going to be belongs to this L1 space, and therefore we can approximate them with some orthogonal polynomials. We are trying to use a Chebyshev polynomial, since they are going to give us the best approximation in the maximum norm that we have for them, and also we can show that it is going to have a spectral convergence for that. Okay, so this is a general recurrence relation for a shifted Chebyshev polynomial, and we can just show that we can approximate any function, any continuous function, by using this Chebyshev polynomial, and it will be exact at the Chebyshev-Gauss-Lobato points if we use in this expression here. In this expression, we're going to have the h, which is going to be constant. We have the discretized value of the function at the collocation point, the Chebyshev-Gauss-Lobato points, and we are going to have a vector of including a vector that it includes all the Chebyshev polynomials. Since the fractional derivative operators is going to be linear, we can just implement it from both sides of that equation, and we will end up to having this operational matrix of fractional order differentiation D, which is basically going to be constant regardless of the choice of the x. And if we multiply any discretized value of the function at that collocation point, it is going to, by this matrix, it is going to give us the discretized value of the fractional order derivative of a function at that points, at those points, basically. To be able to fully discretize the original problem, we need to have some discretization operator, and that is for the sake of simplicity and readability that we are defining as operators. The full details of these operators is being provided in the paper, and we are skipping those in this presentation to save time. But following the method that we propose in this paper, we can just show that the discretized solution of the fractional order system, the LTI system, is going to be given by this equation. and the t has been defined by using those discretization operators. Next, what we need to do is discretize the cost function. And to do that, we are using the quadrature method, and we can show that using those discretization operator, the cost function can be discretized in this form. And then since everything has been turned to an algebraic equation, we can just use the first order condition for that and try to obtain the lambda, and it will be followed by obtaining the control input, the optimal control input, which is given in this expression. So this is going to be a closed form solution for the finite horizon that doesn't require to have any nonlinear programming. To check the advantage of the solution, we're just having this simple problem. And this problem, which looks like very simple and easy cheesy for like a classic controller, but it turned out that it would be difficult for fractional order system, like just a single dimension actually fractional order system. And there have been a lot of literature that they use this example as an example for the method, and they show that the performance of the method. And we do the same thing. We try to solve that problem for different values of alpha. As you see in this picture, we find the optimal value for the x and u, and this black line is associated with the alpha equal to 1, which we have an analytical solution for that, and we compare our numerical solution with that analytical solution. And this table, we show that the results of our paper for different values of alpha compared to the other works, and we can see that our method, it works better compared to the other ones, and we get in the better result. And we just use a 128 collocation points, and they use a larger points for the methods and for the discretization. In summary, what we have done, we actually show the LQR type problem for a fractional order system, linear time invariant. We show that the current method, they cannot obtain the optimal solution without using a nonlinear programming method, and they are also suffering from the linear convergence. But by the method that will be proposed, we can find the solution explicitly and in the closed form, which doesn't require to have any nonlinear programming. And at the last property is that it is going to have the spectral convergence. Thank you for watching this presentation, and hopefully I can answer some of your questions in the conference day. Bye.